So my dear students, in this video now we are going to learn about the preparation and the properties of the pyrimidine. Pyrimidine structure is like this. Look here, and we can call it as the 1,3 diazine. Okay, na? It contains two nitrogen atoms at the third and first position of the benzene, so we can call it as the 1,3 diazine. First of all, we go for the preparation methods. Among them, first one is the preparation of the pyrimidine by using a Melanic ester. You know the Melanic acid, no? CH2 COOH and COOH, and if you write H and HA, this becomes the malonic acid, but here we are taking the Melanic ester, so we write like this. One alkyl group we write here, so now it is becomes diethyl malanoate. Sorry, diethyl malanoate. Diethyl malanoate. Okay. Here, if we treat this diethyl malanoate with urea, urea formula is NH2CONH2. So we write NH2 for convenience like this, HNH. So what happens here? Look here, water goes outside like this. This is very simple method. So 2 molecules of water goes outside. 2H2O. As a result, what happens? Look here, CH2 C double bond O, C double bond O, NH, NH, and CO. Okay, otherwise we can write like this, no? Here one more, what is that? CH2, NH, NH, CO, triple bond O, and CH2, and we have one more C double. So this undergoes tautomerism and exists like this. Two comma 4,6 trihydroxypyridine. Trihydroxypyrimidine. Two comma 4,6 trihydroxypyrimidine. If it is treated with the phosphorus oxychloride, in the place of hydroxy groups we get the chlorines. So here we get the 2 comma 4,6 trichloropyrimidine. If it is reduced with zinc amalgam, reduction occurs. What happens? And chlorine will be substituted with hydrogen. As a result, we get the pyrimidine. We get the pyrimidine. Okay. So this is very simple method to prepare the pyrimidine. Very simple method to prepare the pyrimidine. Diethyl malonate, and this is urea. Okay, Then we get the 2,4,6 trihydroxypyrimidine. On treatment this with the phosphorus oxychloride POCl3 or phosphoryl chloride, we get the pyrimidine. Okay. Now we go for the second preparation method, that is the preparation of the pyrimidine by using the malic acid. So we can remember the formula of the malic acid if we remember the formula of the succinic acid. Okay, now succinic acid, in succinic acid we have 4 carbon atoms, and it is a dicarboxylic acid, COOH and COOH. So this is the, and that means here we write CH2 and CH2, that becomes succinic acid. So here we write one CH2 and we put one H, and look here, if we write 2 hydrogen atoms here, that becomes succinic acid, no? But in the place of hydrogen we are writing one hydroxy group, so now it becomes the malic acid. So this is malic acid, and if it is treated with the concentrated H2SO4, it loses the water molecule and carbon dioxide, and gives us what is that, CH2, COOH and CHO. This is known as the, look here, this is acetic acid, no, CH3COH, and in the acetic acid we are substituting formyl group, so it is known as the formyl acetic acid. If this formyl acetic acid is treated with urea formula NH2CONH2, no, we get a condensed product. So we write the product like this, look here, CH2 C double bond. We write the formula acetic acid once again here like this, and we write the formyl group like this, and I write the urea once again, H C double bond O and NH2. So here water goes outside, and here also water goes outside, and as a result we get this condensed product, CH2 C double bond O and NH C double bond O and CH double bond N. So like this, no. Now this undergoes tautomerism and we get this one. Okay. So here one hydroxy group and here also one hydroxy group we have. And if it is treated with the phosphorus oxychloride, we get the dichloropyrimidine, chlorine and chlorine. So this is known as the 2,4 dichloropyrimidine. And if it is treated with the hydrogen gas in the presence of palladized carbon, that means palladium is coated on carbon, then we get the what is that, pyrimidine. Chlorine will be substituted with the hydrogen atoms. As a result we get the pyrimidine. Malic acid. Malic acid can be considered as the product of the succinic acid. If we remove one hydrogen from succinic acid and substitute a hydroxy group, that becomes the malic acid. On treatment with the concentrated H2SO4, it gives us the formyl acetic acid. Formyl acetic acid on treatment with the urea, this is urea, NH2CONH2 urea, we get the 2,4 dihydroxypyridine. This on treatment with phosphorus oxychloride gives us the 2,4 dichloropyrimidine. This on reduction with hydrogen gas in the presence of the palladized carbon gives us the pyrimidine. We discuss about the third preparation method, that is the Pinner synthesis. In Pinner synthesis we make use of the 1,3 diketone and we allow this 1 comma 3 diketone to react with either amidine or guanidine or urea or the thiourea, and according to this second reactant we get the pyrimidine derivative. So as a best example for 1 comma 3 diketone, we may take the acetyl acetone. We know the formula of the acetone, that is the CH3 C double bond O CH3. No, this is the acetone, and in the place of one hydrogen, if you write what is that acetyl group, that becomes the acetyl acetone. So this is CH3CO group is known as acetyl. No, so now we call it as the acetyl acetone, and we know very well that this undergoes tautomerism. No, so we can write it's a tautomeric structure like this. Look here. So this is the tautomer of the acetyl acetone. Okay, now first we write the different products when it reacts with the different other reactants. So first of all we take the amidine. So in amidine we have C double bond NH and NH2 group. This is simple amidine. Okay, and here we have one hydrogen. No? So this is amidine. No? So one this hydrogen and this OH group goes outside in the form of water, and this two hydrogens and this oxygen goes outside in the form of water. So here two water molecules goes outside. As a result, we get the pyrimidine derivative. So here what is that? 1 2 3 4 5 6. So 3 comma 6 dimethyl pyridine. Next we make use of the what is that guanidine. Okay, now guanidine structure is very much similar to the amidine, but here in the place of this hydrogen we are having the one more NH2. This is guanidine. So here we get this product. So here we get NH2. So 2 amino 3 comma 6 dimethyl pyrimidine. So this is 2 amino 6 dimethyl pyrimidine. Next we make use of the urea, that is NH2 C double bond O NH2, and for convenience we can write this as the hydroxyamidine. So we can consider urea as the hydroxyamidine. So here what happens, we get this product. So in the place of amine we get the hydrox group. Okay, so this is hydroxy, so 2 hydroxy 3 comma 6 dimethyl pyrimidine, and we may take the thiourea also, NH2 C, in the place of oxygen we write S, so it becomes the thiourea. So we get this product. So its name is what is that, 2-thiopyrimidone. 2-thiopyrimidone. So like that, we get the different products according to the second reactant. Discuss about the fourth synthesis method, that is the rim-free hull synthesis. In rim-free hull synthesis, we make use of the alpha butyl melondiamide, alpha butyl melondiamide, and we react this with ethyl format in the presence of the sodium ethoxide. Sodium ethoxide in an ethanolic solution. And we get 5-butyl 6-hydroxy pyrimidine, four one, and at the third place we are having hydrogen, so 4 3H1. Okay, now we take the reaction look in. So we know the melanic acid, that is the CH2 C double bond CH2 COH, no. So in the place of one hydroxy group we write the NH2, that becomes the melondiamide. So this is melondiamide, and if you write one butyl group at alpha position, that becomes the alpha butyl melondiamide. So this is alpha butyl melondiamide. Okay, now here we have to take the ethyl format, no, HCO C2H5. So we can write this like this, no, C2H5 and O, one H here and C double bond O. Okay, then what happens here, one H, so we write this one like this, no? So one ethyl group and hydrogen goes outside in the form of ethyl alcohol, and these two hydrogens and oxygen goes outside in the form of water. As a result, this is C double bond O and NH, and look at this, at this carbon we are writing C4H9, and what is that? Just sorry here. Okay, so yes, and look at this mandro tautomerism, and we get so this is 5-butyl 6-hydroxypyrimidine 4,3H1. My dears, now we discuss about the fifth preparation method, that is the aza-Wittig reaction. We know very well that in Wittig reaction, carbonyl compounds reacts with the triphenyl phosphine oxides, and we get the ketones, no? Sorry, alkenes. So here in azabatic reaction, a double bond is formed between carbon and nitrogen. So that's why here we call this reaction as the azabatic reaction. So here we make use of the benzimidines. So we know very well that this is imidine, and if we write the phenyl group here, that becomes the benzimidine. Okay, na? So here we write the 6H5. Now it is benzimidine, and we react this benzimidine with what is the triphenyl phosphine oxide, C6H5 taken 3, and this is triphenyl phosphine, and if you write oxygen, that becomes the triphenyl phosphine oxide. Triphenyl phosphine oxide. Okay, so first of all, what happens means water goes outside, 2 hydrogens from here and 1 oxygen from here goes outside in the form of water, and a double bond is formed between this phosphorus and the nitrogen. And here we are having 3 phenyl groups. So this is known as the phosphogene product, phosphogene. And then it is treated with the, what is that, cinnamolide or alpha beta unsaturated aldehyde. Cinnamolide, na? So here we will put C6H5. So this is known as the cinnamolide. So here what happens means water what is that, triphenyl phosphine oxide goes outside. Look here this oxygen combines with this one and goes outside in the form of water. As a result, a double bond is formed between this carbon and this nitrogen. Okay, and here we have one hydrogen, I forgot to write. So here one hydrogen is there, and here phenyl group is there. Now when we oxidize this one, cyclation takes place, oxidation. So water goes outside and cyclation occurs. So okay, as a result we get the pyrimidine derivative. Okay, this is pyrimidine derivative. So 2,6 diphenyl pyrimidine. We discuss the chemical properties of the pyrimidine. Pyrimidine is less basic than the pyridine and pyridine, and we know very well that basic strength of an base is proportional to the its pKa value. Here the pKa value of the pyridine is 5.6, pKa value of the pyridine is 2.33, and pyrimidine pKa value is 1.3. That means it is less basic than these two compounds. So basic nature decreases in this order. Okay, now we discuss about the aromatic nature. Here aromatic nature can be easily compared by looking at the resonance values. Here the benzene resonance energy is 36 kilocalories per mole, and pyridine resonance energy is 31 kilocalories per mole, and pyrimidine resonance energy is 26 kilojoule per mole, 36 and 26. And here the pyridine resonance energy is 12.3 kilocalories per mole. That means Pyrimidine is less aromatic than these two compounds, and it is more aromatic than pyridosine. Here we can see the resonance structures of the pyrimidine. Here in these structures, we can observe that the positive charge is present on the carbon atoms and negative charge is present on the nitrogen atoms. Look here, a negative charge here is present, and here in the structures also negative charge is present on the nitrogen atom. So we can say that electrophilic substitution mainly occurs on the nitrogen atoms and rarely occurs on the carbon atoms due to the less electron density on the carbon atoms. Okay, and carbons generally involved in the nucleophilic substitution reactions as positive charge appears on the carbon atoms. Okay, na? Here positive charge appears on the fourth carbon. This is fourth carbon, no? 1, 2, 3, 4, fourth carbon, and what is that? Second carbon in the structure, second carbon is there, and in this structure on sixth carbon we are observing the positive charge. So 2, 4, 6 are prominent places for the nucleophilic attack. Okay, as we have learned that carbon is not getting any negative charge on the in the pyrimidine, no? So that's why rarely it involves in the electrophilic substitution reactions at the carbon atom. So for the electrophile to be substituted on the carbon atoms of the pyrimidine should possess electron donating groups, like I have written in a rank manner, that is withdrawing. So here it has to possess the electron donating groups like a hydroxyl group and amine group. Then only it easily involves in the electrophilic substitution reactions. Here only bromination occurs. This is the pure pyrimidine. So a pure pyrimidine involves only in the bromination, that too at a very high temperature in the presence of the nitrobenzene. Okay, na? So here OH is electron donating groups. So here this one undergoes nitration or sulfonation or other electrophilic substitution reactions very easily, and the pure pyrimidine does not participate in the nitration, sulfonation reactions and alkylation reactions. Okay, now we go for the electrophilic substitution reactions that occur at nitrogen. This is the reaction with acid. This is dilute acid. So when we use dilute acid, only one protonation, single protonation occurs, or monoprotonation occurs. And whenever we use the very concentrated acids, then only diprotonation occurs. Okay, and diprotonation means protein will be substituted on the two nitrogen atoms. This is known as the diprotonation. Next one is the alkylations. So substitution of alkyl group is known as the alkylation. For this purpose, we use the methyl iodide in the presence of the methyl alcohol. So here we get the enalkyl pyrimidine. And the next one is the oxidation. When this pyrimidine is subjected to the oxidation with oxidizing agents like the hydrogen peroxide or peracids, we get the pyrimidine N oxide. This is known as the pyrimidine N oxide. Pyrimidine N oxide. So now here we can see some nucleophilic substitution reactions. This is the reaction with the hydrogen. So one hydrogen from this hydrogen is substituted here, and the remaining NH group is substituted here. So it is like some addition reaction. Okay, and then after this bond breaks here, and we get the amidine group here, amidine and hydrogen group. So in the presence of H plus ions, this one undergoes to cyclization, and we get the ultimately the pyrazole. Okay, so what happens means here this H plus ion attacks here. As a result, this carbon gets the positive charge. Okay, and this electron pair of this nitrogen atom will be attached to here. As a result, we get the pyrazole ring. Okay, next reaction with the Grignard reagent. In Grignard reagent, magnesium gets positive charge and bromine gets negative charge. Halide gets negative charge, and in the same way, alkylar groups gets the negative charge. So first of all, addition reaction occurs. So MgBr will be substituted here on nitrogen atom, and the alkyl group or phenol group will be substituted on the carbon atom. So in the presence of H plus ions, this undergoes hydrolysis, and ultimately we get the 4-phenyl pyrimidine. This is oxidation with KMnO4 in the presence of the acetone. Okay, so whenever we hydrolyze this one, in the place of the same MgBr, NH comes, a hydrogen comes. So with KMnO4 oxidizing is in this H, and this H will be removed in the form of the water. Next reaction with the phenyl lithium. So it is similar to this reaction. Okay, next one is the Chichibobin reaction. So Chichibobin is a nucleophilic substitution reaction. In this reaction, it is treated with the sodamide in the presence of liquid ammonia. So here amine group will be substituted on the 4th position. Next one is the reduction reaction. So this pyrimidine gives different products with a different reducing agent. Here we are taking simply one example. So when it is treated with the sodium, it undergoes reduction and we get the hexahydropyrimidine. This undergoes tautomerism, ring cleavage, and we get the unstable imine. So this is about the reduction of the pyrimidine. So these are some reactions of the pyrimidine. Thank you for watching.